In this video, I go over a project done in Maple. It shows an example of a geometric interpretation of an eigenvalue vector. Let's get started. In this video, we go over an example of a marble rolling along a surface described by this potential energy expression. What does this potential energy expression look like? We can plot it using a contour plot. Where it is darker, that is higher in the surface. Where it is lighter, that is where it's lower in this bowl. What is a contour plot? A contour plot is basically a series of implicit plots where we make sure the potential energy expression is constant along the lines. Here's how it looks in 3D. As you rotate it, you can see that it is curved at the bottom and it basically looks like a cup. So what we're going to do is we're going to use dsolve to solve for its position and momentum as a function of time. Since this is a two-dimensional problem, I'll write these out as vectors. Here's momentum and position, and here's the expression for how to calculate the force in each direction. Notice again, the force is the negative gradient of the potential. If we put in the fact that x and y are given by this r sub x of t and r y sub t, our force vector looks like this. Hence our ODEs in the vector format look like these. Let's give our marble some mass. Let's set the initial position at t equals 0 of the marble given by the components of the r sub 0 vector, and we'll give the object no momentum. We solve the equation using dsolve, providing it the ODEs and the initial condition equations. Then we make a function out of the results that we get, which we have to evaluate from our solutions. Now let's make a plot of our marble as a function of time. We'll pass it, again, the initial position and various times. We can animate this plotting function and include the trace so you can see that it leaves a mark of where it was as it travels along the bowl. A reminder, an animation is a sequence of plots. The advantage of the animate procedure, it does not include other options which are difficult to mimic by just using sequence of display. And here's the path that it traces out. So now we get to the point of this exercise is to how do we geometrically interpret the eigenvector? We ask the question, is there a special location for which if we start the motion at that location, the marble simply rolls down straight to the equilibrium point and back up again? To do this, we will create the H matrix, which is really a matrix of the x and y components of the force. So these are the coefficients here, which means the force vector is h times r. Let us calculate the eigenvalues 1 and 2 and its associated eigenvectors 1 and 2. We can normalize these eigenvectors and remind ourselves that the whole idea of an eigenvector is that h times the eigenvector is equal to some multiplier of the eigenvector back again. Since h times r is the force of the marble, if we give the marble the eigenvector for its initial position, then all subsequent positions for the marble is some scaled value of the eigenvector. You can see this in the animation of the eigenvector as its initial position versus time. When I click on it, what it does is it's in a continuous position that is scaled value of the initial position, which is the eigenvector position. In short, this is its path for the two eigenvector initial positions. These two eigenvectors are the special vectors for which the force applied on the marble always produces some position which is a scaled value of the initial position. This was an example of a physical dynamical system which included several types of plotting and animation.